Consciousness is one of the deepest mysteries of science. How does subjective experience arise from the physical brain? Among the many theories, one of the most controversial and intriguing is the orchestrated objective reduction, or Orch-OR, proposed by Roger Penrose and Stuart Hameroff. At its core, Orch-OR suggests that consciousness is not just a product of classical neuronal activity. Instead, it emerges from quantum processes inside tiny structures called microtubules, found in every neuron. According to the theory, these microtubules can maintain quantum coherent states, and these states undergo a special kind of collapse called objective reduction, linked to fundamental properties of space and time. This collapse, orchestrated by the brain, supposedly gives rise to conscious experience itself. But while the idea is fascinating, it has been met with intense criticism from both neuroscience and physics. The biggest challenge is the question of quantum coherence in a warm, wet, noisy brain. Quantum states are notoriously fragile. In everyday conditions, they tend to collapse almost instantly. Critics, including physicist Max Tegmark, calculated that quantum superpositions in microtubules would decohere in a trillionth of a second, far too fast to affect neuronal activity or thought. Proponents of Orch-OR, however, argue that microtubules may be special. They suggest that ordered water inside microtubules, the arrangement of tubulin proteins, and even certain vibrational modes could protect quantum states long enough to be biologically relevant. Recent theoretical models, like those proposed by Mavramatos and colleagues in 2025, treat microtubules as tiny quantum cavities that could sustain coherence for microseconds, a small but potentially significant improvement over earlier estimates. Even if microtubules can maintain coherence, there's a second challenge. How does this microscopic quantum activity translate into neuronal firing and conscious experience? Critics argue that there is no direct evidence that microtubular quantum states influence action potentials, synaptic, release, or brain-wide network dynamics. Orch-OR suggests a cascade, where quantum events in microtubules are, orchestrated to impact neurons, but these mechanisms remain hypothetical. No experiment has yet measured this effect in living neurons. Another major claim of Orch-OR involves anesthesia. Hameroff and others propose that anesthetics work by disrupting quantum states in microtubules, which would explain the loss of consciousness. While some experimental data show that anesthetics interact with tubulin, critics point out that anesthetics have, many classical effects on ion channels, receptors, and membranes. So, it is actually unclear whether quantum disruption is necessary or sufficient to explain unconsciousness. There's also the objective reduction mechanism itself, which is, unique to Orch-OR. Penrose proposes that when a quantum superposition reaches a certain threshold of gravitational self-energy, it spontaneously collapses. Now, while recent experiments in superconducting circuits by Tag and Reed in 2025 provide some tentative evidence for gravity-related collapse, this has not been observed in neurons or microtubules. Honestly, whether this process actually occurs in the brain still remains speculative. Philosophically, Orch-OR is definitely attractive. It tries to explain the binding problem, which is how disparate sensory inputs form a unified experience, and it also addresses the so-called hard problem of consciousness by linking subjective experience to a fundamental physical process. But, critics argue that even if these quantum events do occur, there's just no proof they are necessary for consciousness. Standard neuroscience, focusing on synapses, networks, and neural oscillations, can account for many cognitive functions without invoking quantum mechanics. Recent theoretical developments have tried to strengthen Orch-OR. Models propose self-organized criticality in microtubule networks, quantum resonance effects, and energy maintenance mechanisms to protect coherence. While these ideas make the theory more physically plausible, they remain unverified in living brains. No experiment has yet shown microtubules maintaining coherent quantum states for long enough to influence cognition, nor OR occurring in neurons. In short, Orch-OR remains one of the most ambitious and controversial theories of consciousness. It is scientifically exciting because it attempts to bridge neuroscience, quantum physics, and fundamental physics. but it is still speculative. Major criticisms focus on three key points. Decoherence. Quantum states are fragile, and the brain is a noisy environment. Causal link. No direct evidence yet that microtubule quantum states affect neuronal computation or conscious experience. Testability. The predictions of Orch-OR, including objective reduction in neurons, have not been experimentally verified. Yet the theory continues to inspire research. The 2024 to 2025 models of microtubule coherence, quantum cavity effects, and collapse experiments in non-biological systems show that parts of Orch-OR are becoming increasingly scientifically testable. Future experiments might detect quantum coherence in microtubules, measure OR-like events in biological contexts, or even, demonstrate causal links between these quantum processes and cognition. For now, Orch-OR stands as a provocative bridge between physics and consciousness. It challenges us to think beyond classical explanations, reminding us that the brain may hold secrets at the edge of what we currently understand about reality itself. If you enjoyed this exploration of the quantum mind, subscribe for more videos on cutting-edge neuroscience, quantum physics, and, the mysteries of consciousness.